and for the excellent conference. My talk will consider the groupoid-related rings, which in our setting that is not necessarily unital, and so we're going to study the structure of groupoid-related rings. This is a joint work with Zuhong Zhang and Zuhong Zhang. Let's first recall some basic definitions of groupoid. A groupoid is a small category such that every morphism is invertible, and let G denote a groupoid. We use G up to 0 denotes the object of the category, and the G1 a groupoid, and the G0 denotes the set of the object of the category, and the G1 denotes the morphism of the category, and we use Gxy denotes the morphism which starts from X and ends at Y for all objects from G0. So we use Gx denotes the morphism the automorphism of the object X. So for the groupoid case, this is always a group. And sometimes we use for any G from the morphism set of the category, and we use the SG denotes the domain of G, and the ring RG denotes the codomain of the G. And a groupoid is called a connected if for all X and Y, the morphism set Gxy is not empty, so it's just as the meaning of the connections. And the other extreme is totally disconnected. Namely, for any different X and Y, there is no morphism connecting them. In our talk, our breeding, our groupoid always taken to be connected. A subcategory H of G is called a subgroupoid if H itself is a groupoid, and in the case that H, the object set of H, equals to the object set of G, then we call H is white in G. Now we can define what is a normal subgroupoid of G. So for being normal, H first should be totally disconnected and white. And for any H belongs to the groupoid G, then this equation holds. Namely, the computation of any element from H goes to the subgroupoid H. This is because H is always white, so for any G, this source of G must belong to H. So, and H consists only those disconnect parts.
What does the bar mean?
Okay, bar. Oh, sometimes we use this notion denotes the morphism group of X to X.
The second criterion, so small g belonging to strip G. So is it G1 or like, what is it?
Okay, I think this should be G1. Yes, right. Thank you. And then, so we can define the quotient of a groupoid in a straightforward way. The same as the situation in the group case. Now if we come to the groupoid related ring. Let G be a groupoid, and here we take G to be always to be connected. Otherwise, so if A is graded by a groupoid which is not connected, then it's easy to see that A is a direct sum of some connected groupoid graded ring. So if G is so here G is connected and A can be written as the direct sum of the homogeneous component of A, which this sigma comes from the groupoid G. And we don't assume that A is unique also. In fact, in our talk, the most interesting part is non-unital case. And we hope this A is a groupoid graded ring, and A sigma, here A sigma is an additive group, and for any sigma tau and sigma from G, and A tau times A sigma is a subset of A tau times sigma. So this later part is same as the group graded case. In the case if tau and sigma equals to A tau times sigma, for all tau and sigma which is composable from G1 and they are composable, then we call A is strongly graded. In here we have slightly different with the classical case, namely the group graded case. In group graded case, we don't have we don't need to add this assumption because any group element is the group multiplication is a binary multiplication. It's a binary operation, and here the groupoid cases for the groupoid case the multiplication of groupoid is only a partial binary operation. So sometimes we cannot multiply some of those elements. And in particular, if we pick an element from G0, namely an object from the category, and so this AX, so this means the ring generated by the homogeneous element come from this okay, right here, sorry. So this comes from sigma comes from GX. GX is the morphism from G to G from X to X. Then this is clearly a group. GX group. This GX is always a group, and it's GX graded ring. So then we come to the classical case, GS graded ring. So this is a summary of the whole group graded ring A. In particular, for the group, for the connected groupoid, it is clear for any x and y, we have we have gx always isomorphic to gy for any two different objects. Since the G is connected, G is always connected. So sometimes we refer this group as the tactical group of the groupoid G. So then we can define the G graded modules in the usual way, and M is also a diagram of these homogeneous components, and M is first the A module, and then it can be decomposed as a diagram of the homogeneous components. So this is nothing different from the group graded case. To treat the non-unital ring, we need some further definitions, and take any element from a graded module M. So M clearly can be written as the sum of some homogeneous element, and then we can define the support of M in G. Okay, I forgot to write a curly bracket here. So the support of M is just taking all those gradings out. This formula set, we call it support of M. And in our setting, we need another definition or a better one to work with. It's called the objective support of M. The objective support of M is the set. So we have the support side, and for any sigma from the support side, we take the source and the range of the sigma, and this forms the new set which belongs to the G0. This belongs to the object of G0, and so this is called objective support of M. And of course, this notion can be generated, can be defined returning to any subset of the graded module M. Let S be a subset, so we define the support of, we can define the support of M to be this set. So we take M takes from the set S, and we can consider the objective support of M. So this is what we need. Now that we have a notion which is a generation of the unital rings, and we call A is an objective unital ring if giving a subset S of A, any subset of A with finite objective support, then there exists an element E which depends on the subset S, such that E is a locally unit. So here, clearly this is we have a notion, classically we have a notion of locally unit ring, and this A is clearly a locally unit ring, but here we put more assumptions on this ring to overcome some technical difficulties. So so we should know here we just assume that S is objective is objective support, finitely objective support, but we are not assume that the real support or the classical support to be finite. This set is not assumed to be finite.
You want E to be idempotent? Or?
Oh, yes. So here we have some basic properties of the objectively unital rings. So first, it's easy to see that A is unital if and only if the object set of the groupoid G is always here. This G should be this G. So this, if we don't have this objectively unital, this notion of objectively unital, then we don't have this equivalent relation. In general, if A is locally unital, that means the grading is finite. And if we take an object from the grading G and a Gx, as we mentioned, this is a graded ring, graded by this typical group, and also this is a unital graded ring with a homogeneous element come from the if we have a zero here, this would take this group. We have zero component of the identity. If we write it additively, and we take the identity the identity of the group, and this unit element should come from here unit should come from the zero components. So then we have any local unit of A, so can always be chosen as a sum of those local units in this with this not finitely support, but it's only one object support set. And support H is a normal subgroupoid of G, then the graded ring, if we take the quotient of G over H, is also objectively unital. And we can define the morphism between two objectively unital rings. If take another objectively unital ring B, a morphism of morphism being to objectively unital means if phi maps every local unit to the local unit B. Here, the local unit here, I mean the local unit means those elements are the sum of those elements, but not in the general sense. And A can be decomposed as can be written as the direct sum, direct limit of the unital subrings. So, and those unital subrings has finite support or objectively support. Okay, those are the properties we can get easily from the definition of this unital ring. And now we're going to define what is free and projective modules. Let M be a G-graded module. First, we should define this operation. We call it shifting of M. Pick a sigma from the groupoid G, and so we use the M sigma shift of M. Use this symbol to denote the sigma shift of M, and which denotes this denotes this subgroup, this module. Namely, every homogeneous component after shifting the tau homogeneous component of level tau in this shifted module equals to the homogeneous components of the original M with the level sigma inverse times tau. Because this in the groupoid case, groupoid graded case, those sigma tau can be not composable. So then we need to add this assumption that they are really, we can compute the multiplication of sigma inverse times tau. And otherwise, if they are not composable, we put it 0. So we should be careful here that in the group graded case, we always have this simple then shift it and then shift it back in the group or in the graded case. But here we cannot do this. When we shift and then shift back, we get smaller modules. We cannot get back the whole. Okay. For the group cases, we always have this equals to the original M, but in the groupoid graded case, it's always okay. If this equation in general, this set is contained in this set. Because here the operation, this operation kills lots of components, which is not compatible with sigma.
Sorry, Professor. If For group case, for the graded model, the safety is given by multiplication. So here I'm wondering, here we use the inverse of sigma. Is that we use sigma pound? It's okay. So
it's just a setup. You can use sigma or sigma inverse, then you go different direction.
I see.
This. Now we can define the free and the projective modules of groupoid graded rings. It is well known in the group graded case. So a free module is a shifting. Okay, it's writing in this way. So this is pick some element from the grading, and we shift the modules and put it together. Then we get the definition of the free modules, but it is clear that those modules, if we forget the shifting, then this is a free module in the classical setting without grading. But in the setting of groupoid graded case, we take the similar definition. So M is free if it is isomorphic to a direct sum of the module of the form A with a shifting. So here it's also if R is a G graded with the group graded, and the free module is the direct sum of the shifting, but those copies are all isomorphic to the underlying R. In the groupoid case, those shiftings are not free in the non-graded case. This is not free. And so then we have the definition of projective module. In this setting, it's just as a direct amount of a graded free module. In general, a graded free module is not a free module in the Euro sense, in the classical sense, but it is always a projective module. So we didn't get anything weird. It's still projective. Now we have a category to work with. So the category of the underlying ring is finitely objectively supported unital ring A, and we can consider the modules, the graded modules, the category of graded modules of A. Let A be a G graded ring and H be a subgroupoid of G, and let M be an H graded AH module. AH means A. If we take out, because H is a subgroupoid, if we take out all the homogeneous components come from H, then it forms a subring of A, and we can consider AH modules. Then we can take the tensor product of M with A over this AH, and this is a G-graded A module. And the grading, we define the grading in this way. And this tensor, we want to show what is this is a G-graded and how we define this grading. And take a sigma from the G, and this grading equals to here. If this M can be written in this form, and then so the Mi come from mu I. This mu I belongs to H, and Ai comes from A alpha I. And this element, we say this element is of level sigma if this for each I, this multiplication equals to the sigma. Then we have a tensor product in this category, and we can tensor a module which is H-graded and give it and get a new module with G-graded. And we use this tensor product to define two functors. The first functor we call it I, which is come from AH graded, come from the AH graded, the category of AH graded modules, and to the category of G graded modules. This is H graded and okay. Explain this notion. This is AH. The underlying ring is AH, and H graded the category of H graded AH modules, and this is G graded A modules. This I and R is another operation come back from G-graded A module, the category of G-graded A modules, to the category of H-graded AH modules. The operation here, the operation is very clear. It's defined here, and this means we just take the homogeneous component. Here we take a module M, and we take all the homogeneous component from H, and we form a new module, which is clearly an AH module. And those two functors defined above are joined with a junction max defined here. So it's epsilon and eta. So, and the epsilon comes from epsilon. A, so there's a missing here, and to M, and eta from T to the TH tensor AH tensor A. the operation is any element here, we just take the any tensor. Here here, in fact, we take the multiplication m times n, and the eta here we take the tensor of them. So then we can show that this two functors is adjoint higher, and the adjunct, and we can construct the adjunction map here. Then we can write down the date theorem. This is a well-known theorem. It says in the classical case, and in the group graded case, if A is a ring which is strongly graded, G graded, G is a group, and then G, the category of A module is isomorphic to the, is equivalent to the. Let me write down the classical case. A is G strongly G graded that is equivalent to the A0 the category of A0 modules. A0 means the homogeneous component of of level 0. And this is the classical case or group graded case. We generate this theorem to the groupoid graded case, namely if A is objectively unital G graded ring and H is a normal subgroup of G, we assume that if we change the grading of A, we consider G as a G modulo H graded, and if this grading is strongly or this ring is strongly G modulo H graded, then if and only if those two functors I and R are mutually inverse equivalent of the category this category and this category, those two categories are equivalent via those two junction maps, and this we can reduce the theorem says that in the classical case we can reduce our consideration. If G is strongly graded, then we can reduce namely we can reduce this graded the module of G graded module to the module to the A0 module. And here in the and here this is not a graded module, this is just classical module. So we can forget the grading here if A is strongly graded, and then this theorem is very powerful here. So we can reduce in the strongly graded case we don't need to bother with the grading. Lots of problems reduced to the non-graded case. In the groupoid case, we have the similar situation, but we cannot reduce to the most simple part. Namely, we cannot totally reduce the grading, but we can from a bigger gradient goes to a smaller gradient. In particular, in case if G itself is strongly graded, then we have this this corollary. Then the A is objectively a unit of strongly G-graded if and only if the functors I and R are mutually inverse equivalent of the category AZ. I will explain what is this Z. AZ and the original category of category of G-graded modules. Well, what is this Z? Z is we have in the group case. So that's in the group case. So we have this theorem category of graded module reduced to the category of ungraded, and also we can see it as a module graded by trivial group. So here, this is also, so this is graded by trivial group. Okay, this is a smaller group in the trivial group is the smaller group of A for any group. And here, A is groupoid group of gradient. Groupoid graded case. Now A is graded by this groupoid G, and it's strongly graded. Then where should we go? We go to some AZ module. Still, this is graded module. So and the Z is the smallest groupoid in this groupoid, in this bigger groupoid G. Namely, you take any groupoid. For example, we take a groupoid with two objects, and we have a lot of morphisms. So this has this right here, same, and here, lots of maps going between them. So what is the smallest one? The most, okay, we call it almost trivial subgroup. This almost trivial group. Which is denoted by zero, by Z. Is this groupoid? Namely, the typical group. The typical group is trivial. This is the case.
The smallest one will always exist.
Yes, it always exists. in fact, we can have a way to find one. So for example, you take this, we take a more complicated case. We have several points. Okay, this is a groupoid, and we have we pick objects, and for each object we pick a morphism. At the same time, we pick the inverse, right? And so then we form this, and this generates almost trivial groupoid. And so then we were able to reduce things to those kind of things. So they're always trivial, almost trivial capable group. And yes, this is what I'm going to.
I'm just I'm wondering, are there any cool examples of groupoid graded rings arising in other contexts, or where does this have applications?
You want an example for groupoid doing it?
Just like an example of I don't know. I'm just curious about whether there are any well-known things which can be viewed as groupoid graded rings, or just kind of where does it lead to? Because it's
I don't have any nature example, in fact. Nature, we can construct something, but it's not nature.